Let me share my screen. So hi everyone, thanks for joining live today. And for folks who are going to be watching this later on, this is Multimodal Weekly, virtual webinar series hosted by the team at 12 Labs. We've been meeting on a weekly basis over the past, almost 2 years now. And here's some of the topics that we tend to cover on a weekly basis: news research in multimodal and foundation models, innovative application and multimodal in different verticals. We have a pretty active Discord where community members share their relevant projects, video application, multimodal understanding, etc. And then we have team members internally giving talks on how to, use our platform and API. So in some of the recent session, we have a wide variety of speaker persona. We have team members talking about how to work with our embedding solution. We have researchers coming and talk about, everything ranging from benchmarking multimodal models to reasoning for video understanding to generative solution leveraging multimodal content with text and sound. And I think last week we had a couple of users who talk about the experience building on top of API. So for today's session, we'll have two talks, two presentations. The first one is going to be a project called Maya, which is an instruction fine-tuned multilingual vision language model. An ability was conducted in conjunction with the Korea for AI organization. And we have three speakers, Nahid Alam, Karthik Reddy Kanjula, and Surya Guthikonda. So they will cover the first half of the session. And for the second half of the webinar, we'll have Jiamian Wang, currently a PhD student at RIT. He, actually, the second time speaker. Last talk was also about Text-Video Retrieval, so excited to have him back again today to talk about his latest work also on Text-Video Retrieval, leveraging some of the innovation in diffusion model. So quick, let's just go note. Feel free to send your question on Zoom chat, and then I will surface this question to the speakers as they finish the talk. So I will stop sharing my screen and let's see, I will unmute Nahid, Surya, and Karthik, and enable screen sharing. So you guys should be able to go ahead.
Hi everyone. Hi James. Let me share my screen. You see my screen, right?
Yep, you want to see it.
Yep. Yeah. Hi everyone. So I am Nahid, and today, along with me, I have Karthik and Surya, and we all three are going to talk about Maya. And so it is, what is it? So it is actually an instruction fine-tuned multilingual vision language model. The way it was, the name, like you might ask why the name is Maya. So we, beyond our day job / study, we, three of us, we are actually part of this Cohere for AI open research community. And we sometimes share random ideas there. Hey, what if we do this? What if we do that? And then one day I basically shared, I think sometimes in May last year, that, hey, what if we build a multimodal version of Aya, which is, Aya itself is a multilingual LLM. And that's how it sort of like got started, and we're kind of seeing sort of the end result here so far. So I guess, like, if you think of like what is sort of the key challenge, at least at that point of time, some of them might not be a challenge now, but that's debatable. So if you think the existing sort of vision language model, and when I say vision, I blindly generally mean image text. So they typically support like the common, obviously English and maybe Chinese or one more language. And so it's generally limited with 1 or 2 or 3 languages, and they are generally the more common, widely spoken languages in the world, typically, right? And you'll see a lack of like multimodal models that covers less spoken languages or like wider variety of language. And I think if you think of it, like really what is one of the main reason for that is really the lack of quality of open source multilingual image text dataset. So that was one of the problem. And I guess like even if the data sets that are there at that point, or probably even now, they have like sort of like limited cultural context. So I think these sort of like combines why we do not see multimodal model that covers like more than a few languages. So that's what really we wanted to do with Maya, is build this open source image text pre-training data set, so we can build this visual language model in multilingual context, right? So to begin with, what we have built is we have built the pre-training data set in 8 languages. And we Karthik and Surya will talk about it in very detail, like how we have done that. And we have used that to build the first version of Maya that I'm going to show after that. So yeah, with that, Karthik, I hand over to you on the dataset preparation side.
Yeah, thanks, Nair. So for the dataset side, mainly there were few challenges. So we don't actually have a particular dataset that we can think of and use it as multilingual and train. So we initially choose LLaVA architecture to train the model upon. So in the same way, we choose the LLaVA pre-trained dataset because the kind of variation of distribution they have is different. So that variation would be really helpful for the model to understand all the nuances. So that's why we choose LLaVA pre-trained dataset. So if you pick LLaVA pre-trained dataset, it has 558K rows. And within that, there is 2 things called human value and GPT value. So in the human value, as you can see, there will be a detailed description. It could be explain me in detail, point the thing, describe the image in very detail. So such kind of instructions. And for the GPT value, mainly it will be the image caption. So we, for human value, we identified 11 unique instructions and translated them to 7 languages. We are removing English, so there are 7 languages. So we did that with Google Translate. And then we manually back translated and did some verification on top of these 11 translated unique instructions. So for this part, we actually have our team members to use it with ChatGPT and then back translate it, and then also compare with Claude, then Gemini, etc. And after doing such verification, we created the translated human pre-training dataset. Then after if you come to the GPT value, so in GPT value, we picked 30 values per language. So there is 210 samples. So we picked this based on length, based on reading ease, based on the grade level from kindergarten to the K-12. And then we use the same process again, and then we had human verification again. And then we have an eval data set, which we are going to use in the next step. Nahid, can you move to the next one? So, okay, yeah. So in the preamble, preamble is nothing but instruction, which will be used to do the translations. So to use the IR35B model, which is a multilingual model, At that time, it was the very highest capable multilingual model. So we used that to do the machine translation. But in order to do that, all Cohere models or Cohere for AI models, they require a system prompt very well designed to work well. So in order to do that, we created 6 prompts, which are nothing but preambles. And then we already have our eval dataset that we earlier prepared. So with this, we choose the best one by comparing the blue score and n-gram coverage against our reference translations, which we earlier prepared. So after this, we understood which preamble have performed best across all these 7 languages, which we'll see in the next slide. Nahid, next slide.
Yeah, I'm trying to move it. I don't know why.
Okay. Yeah. So in these 2 graphs, you can see the first one is a radar chart exposing how each language, how each preamble is performing for across each language. And you can see a radar chart, which will give you more detailed explanation of which preamble worked very well across all languages, which is preamble 6. So that is our system prompt that we are going to use further to do the machine translation. So next slide, Nahi. So in the next slide, you can see here, so we already have the 558K rows of English LLaVA pre-trained dataset. Now we extracted all the GPT values. The GPT values are nothing but the image captions, which are in English. So we did a batch processing of with the help of API in async, and then we used the IR35B translation model. Then we introduced our best performing preamble and did the translations. So there is certain engineering steps that you need to follow while doing in large scale. So we performed all those, and then we had a pre-training data set available at this stage. Next slide. Yeah, so the kind of preamble that we implemented was, it's a few short example preamble, but in the specific things to consider while translation, we had many detailed points that we just couldn't place here. But if you go to our GitHub, you will be able to find the preambles in detail for each language. So the things that we ensured are the kind of dialect, the kind of wording for each language. So for example, you take a color. In terms of color, you take pink. Pink can be there in English, but pink is not the actual word for different other languages. If you take for French, it is mostly known as rosé. So those kind of references are also very well taken care of at this step. That's it. I'll hand over the next thing to Surya.
Yeah. So once we have created the data set, and then like we're just on one day, like we're just going through the how exactly is the translation has been done, and then to our surprise, we found like some of the images in the data set are kind of toxic in the sense like there are like some violent images, there are some sexual images that are present in the LLaVA pre-trained data set, and like considering it's like most used standard benchmark data set, like academic data set. So we thought, okay, let's analyze it and see like whether is it the case with the whole data set. So we had done the analysis on 2 fronts. Like one is the like a test analysis. So for whatever the test that is present in the whole data set, so we used the toxic bird to find like what are the toxicity levels. Like we have passed whole the data set to the toxic bird, and we have analyzed, and we found like these were the like different labels on like, so if you pass a particular test to the model, it will give us the like different labels like toxicity level, and whether it's obscene, threat, insult, and all those things. So we've played with the threshold levels, and we found like 0.8 is a good threshold, such that it was able to detect most of the toxic test. And like once we have done that, like we have found like 892 samples of it, and like test will only give us the only a certain part of the information, So the main thing we should be looking is the image. So we even did that analysis, like we have used a LLaVA. It's also a vision language model. So it takes kind of a safety policy. So they have around like 7 or 8 categories, and it gives some certain policies on like given this particular image and the safety policy, it will determine like what's the safety rating, like whether it's a safe or unsafe, and what kind of category it is, like whether it's sexual content, threat, or some like racism, something like that. And it will also give us the rationale on why it thinks that it is an uh, it's a toxic image. So we got this particular analysis, like we have passed a whole image data set like 558K to the LLaVA and got these results. And then we were just seeing that like whether it has done the good job or not. Then we found like some of the images are not really the toxic images. So we had done a little bit of like we have done like little bit of analysis on whether the rationale is correct or not. And after doing that, we found like around 7,000 images that are toxic. And in total, like using both LLaVA and Toxic, but we have like 7.5K. Like although it seems very little compared to the 558K, but when we are translating it over multiple languages, it might increase a lot. So, and like this, like we filter the whole data set, and it doesn't contain any toxicity in it. And after that, like we also done a small like verification part of it, where like we also verified that Nahid, can you move to the next slide? Yep.
Yeah.
And one more slide. Yeah. So we also made sure that like what are the translation that was given by the model is pretty good. So we have done a small quality assurance in terms of whether like there is some problem called like sometimes model just keep on repeating the same tokens. So in order to detect that, we have kind of check the reference like English sentence and the corresponding translated sentence, and we checked whether like 2 or more tokens are repeatedly occurring and which is not present in the English sentence. So we checked that, and we found around like 7% of the translations are repetition. So kind of we removed those. And then after that, we also check the like blue score in terms of like what are the translated test and reference English test. And we have done like small analysis on that. Can you move to the next slide, please? Yeah. And like these were the small analysis that we have done. So here like we have done for like all the 7 languages, and like we found the French is the best performing language in terms of like the translation quality, and Arabic was poor. So we have done this, and we have thresholded like some of the data set to remove the bad translation data set. And like this is what we have done in terms of toxicity and translation verification. Next slide. Yeah. Now Nahid will talk about model training.
Hi, thanks, Surya. Yeah, so I think as you see, the team had done like phenomenal work on sort of creating the translation pipeline, and not just creating it, like this repetitive quality and toxicity verification and improvement. So I had the privilege of kind of taking that, and really the first version of my project was to have that data set and build the first the first version of my model, which is really based on the LLaVA architecture. And so if you're familiar with LLaVA, both the vision and language encoders are frozen there. And in terms of the language model, we have used IA 8 billion model. And compared to the original, LLaVA model has actually vicunized the language model. And for image encoder, we have used SIGLIB. There is a multilingual version of SIGLIB that which is what we use. I think it's like 400 million parameter instead of CLIP in the LLaVA model. So we kind of, in terms of the encoder, it was different. And then we played with the fusion layer, which is in LLaVA, it is really, I think, a 2-layer MLP with GLU. So we tried different combination on the projection layer, but we found, at least for the first version, the simplest one was the best. There was not enough ROI trying more complicated projection layer at that point, at least. So that was really the architecture, and we went through sort of like various stages of pre-training. So we sort of like did pre-training in 1, 2 languages as the language translations were like keep coming and coming. And then we sort of like, okay, when the final, all the 8 languages came, we did the whole sort of all the 8 language together sort of training. And you can kind of see our history of experiment. Not all, there were, I think more than 25 experiment in the beginning with our own sort of like personal Google Cloud kind of thing. And then, so once, and after that, like we kind of went into the instruction tuning stage. And really for instruction tuning, we did not create our own data set for instruction tuning. We used the Palo models instruction tuning data set. So Palo is a model from MBZUI, and what they have done is they have translated LLaVA's instruction tuning data set on like 10 languages, I mean like 9 languages, English as is. And we used that same data set. And I think the interesting thing to note here is, I think the instruction tuning original LLaVA dataset is 665K, but the Palo translation only contains like 150K. So if we just compare with LLaVA, we are, in a sense, we are lacking in terms of the volume of dataset. But this was like for the first version, we kind of stopped there. We experimented with like different types of LoRa tuning versus non-LoRa tuning for the instruction tuning time, and we observed certain instabilities with LoRa at that time. So really, I guess at that point, at least GPU was not a big problem. So we said, okay, we don't need LoRa for now because it typically requires playing with more hyperparameters. So we decided to abandon that route. Here, I think we have, I don't know if you guys can see the video demo. So as you see, we sort of asked this question like, what was, I think it's not showing the question, but what is the famous site here in this photo? So it, our model, Maya, basically replies that it's a diamond head crater in the island of Oahu, Hawaii. So, and you can check out, I'll share the link at the end. I think there is, okay, so another interesting thing you'll see. So I think the this demo is really, we are testing these different photos in different cultural contexts along with different languages. But you can also, if you check the demo on the page, I don't know why it's not going next page actually. Yeah, so if I'll share the link at the end, you can, in the actual demo, you can also say, okay, describe this image in French. So although you're writing in English, but you're saying in French, so the reply will come in French language. So you can do that for really all the 10 languages, not just 8, the 10 languages that is, it was instruction tuned. So you'll see that reply. And yeah, I think to wrap up, this is the paper, and you see the team, all the team members' name who helped during this journey. And this was really all unpaid work. Nobody paid any of us anything. So I'm really thankful to everyone in the team. And yeah, and so feel free to check out the paper link and GitHub and the demo. Yeah.
Great. Thanks a lot, Nate, for concluding that the talk with those information. Yeah, so attendees, if you want to have any question for the presenters, please unmute and ask your question. Maybe one question to get started. Sounds like based on your last slide, right? It's big effort for a lot of team members. I assume you allocate the workload depending on each phase of developing Maya, right? There will be people focusing more on the data set collection. There'll be people more focusing on like model training, etc. Can you like just give a high level explanation about like how do you think about like collaboration?
Yeah, I think Karthik and Surya can talk about the dataset sort of side. I think they both of them took the load from me from there, and they can talk about the distribution of that. I think on the modeling side, really, I think that the two pieces were like, I think it was kind of hard to scale that because everybody does not have GPUs. So we had certain members who sort of like coded some piece of the thing, but then they cannot really test because they don't have the GPU. Only one person actually had GPU in the beginning. And then we have some folks who are they are actually on the university. So from universities, they had GPUs and they helped with a lot of like evaluation. I think at the end, it was quite a crunch time in terms of like, okay, we have a few versions of the model, but now we need to evaluate and kind of also like parallelly write things, write the paper and like prepare everything. So I feel like actual training was not very much scale, but I guess like coding and then evaluation, I would say evaluation was really kind of distributed among at least 4 or 5 members. And then on the writing side and like research side, okay, what are the background work and things like that? There are like few members there. So I don't know, Karthik, you want to talk about how you distributed the data work?
Yeah, so basically, initially, the goal was to create the whole pipeline for machine translation. So that was our initial agenda. But to have a collaboration work style, we made sure that we have regular meetings to discuss even on the architecture level of designing the pipeline itself. So that was from there, we started to collaborate on each and everything, made sure all the team members are involved, and we also made sure we take their recommendations, and based on that, people who are interested in taking on a few of the chunks that they really want to show some work and do some dedicated work in that kind of thing. So we used to allocate in that way, but end of the day, we have time crunch because we made 90% of the project in 6 weeks. Only 10% we did it like in the rest of the 2 months. But yeah, so since there is time crunch, we made sure like everybody has their deadlines, and yeah, that's it. That's how we have done. It's mostly making sure that collaboration is happening among the team members, and also taking their feedback as needed and taking the right decisions to take which approach will lead us faster before the deadline is correct. Yeah.
That's good. Another thing I'm curious about. So in the page you mentioned that the data set required multilingual annotation in 8 languages, right? I don't know. I think you covered it, but can you talk more about that process of getting annotation?
Yeah, like for the dataset part, wherever the multilingual annotation, mostly we did machine translation, but irrespective of that, for beginning of like for human values, which are whatever present in the LLaVA pretrain dataset, for those we have used humans to make sure to annotate some of those which are not actually producing good kind of translations by all the respective models like Claude, GPT, and Gemini. So we made sure at those stages, we made sure like humans intervene and do the respective translation accordingly, because that is the most important thing as an instruction. We are sending that initially to the model. Yeah.
So just to recap, you got the images and you use a multimodal LLM to do the initial route annotation, and you like use human review to verify.
Yeah, like
anything.
initially we picked 30 different samples from the entire 558K dataset for each language. So how we pick these 30 samples is based on the reading level. So at each stage, a person can read a sentence at different level. Like if you are a PhD student, you can read a very complex sentence. If you are like in the K-12 school, you can read a sentence at different levels. So these kind of complex sentences and the reading easeability and much more things like this, the kind of like not repeated characters in the sentence. So these kind of 30 different sentences has been picked, and we translated them to different languages, like 7 languages. And we also made sure like human intervention was there to verify these translations that they are of good quality. And later we used this as these 210 samples as our evaluation data set for the preamble that we are going to give to the LLM. So we designed like 6 different system prompts to even get to know that the model could deliver nice translation like of the image caption. To do that, so we have performed this whole process of preamble evaluation, which is like system prompt evaluation. And
Yeah.
you already know the rest of the things like more quality assurance for the token repetitions and etc. Like where the n-gram value or blue score didn't perform well. So we filtered that kind of data set too.
I guess the question probably, James, you're asking is like so basically LLaVA dataset has image and text. So that text is in English. So we translate that. So the process Karthik is describing, we translate that English to those other 7 languages. So in total, we have 8 languages for the pre-training dataset.
Yeah. And besides the LLaVA, you mentioned you also use Palo, right? As
Yeah.
additional data set. So
Yeah, so we only took the Palo's test, the instruction tuning dataset, which is a subset of LLaVA's instruction tuning dataset. So it's not really separate. The reason, so I think this 10 and 8 might be confusing a little bit. So Palo has those 10 languages for instruction tuning, but when we created pre-training dataset, we used 35's API, which did not have 2 of those 10 languages there. So so that's why that is 2 less. Yeah.
Yep. Great. Yeah, so I think, since we probably passed the first half an hour, we can probably conclude the first talk and move into the second talk. Yeah, thanks again, Naif, and the team for presenting this work. I've been a fan of Korea for AI for quite a while, so very excited to see the kind of research, distributed research that that organization has produce democratized access to researchers for the process. excited to see more work from you guys. And look forward. All right.
Thank you.
Yep. So yeah, let's go ahead with the second talk. Jiamian, you ready?
Yes, let me share my screen. Hello, James. Hello, everyone. So let me introduce my recent work called Diffusion-Inspired Truncated Sampler for Text-Video Retrieval. So firstly, I would like to introduce some background knowledge for text-video retrieval. It contains two subtasks. One is text-to-video retrieval, that we, given a text query, we want to search for the most relevant video from a video candidate pool. And the other one is video-to-text retrieval, which is given a video query, we search for the most relevant text from a candidate pool. For the video data, we generally refers to long or short video clips, while for text data, it refers to caption, title, subtitle, hashtag, and etc. So generally, we employ a video encoder and a text encoder to map the video and text data into a joint embedding space, and then we calculate the similarity in this joint embedding space. For the loss function, a popular loss we generally use can be symmetric formed cross entropy, such as popular info NCE loss. The principle of this loss is that we pull the relevant pairs together, and in the meanwhile, we push the irrelevant pairs away from each other. So here below, I provide a general info NCE loss for text video retrieval. For the evaluation matrix, we generally use rank and recall at rank k, such as R81, R85, and R10, which means relevant video values ranks among the first k. And also we employ the medium rank value of the relevant video candidate, and the mean rank value of the relevant video candidate. For the last two, the smaller the value is, the better the performance we have. So let's go to the motivation of this work. One of the key challenges for text video retrieval is that how we can better bridge the modality gap for the relevant pairs. So as you can see by the subfigure A here, we define the modality gap as a random variable, such as delta equals to V minus T. The difference between the video embedding and text embedding in joint embedding space. So our next goal is how we can model the distribution of the delta in this joint embedding space. And we try several different strategies. The first one is that we posit a fixed prior for this random variable delta, that it follows a Gaussian distribution with different variance. And we find actually this method does not work very well, since the fixed prior is not that flexible. And naturally, we raise a question that since the diffusion model has a very strong modeling capacity in learning the distribution, can we learn a diffusion model in this strong embedding space to capture the distribution of the delta? So here we introduce a Manila diffusion model in this strong embedding space. So as you can see, this is corresponding to a forward process of diffusion model that we gradually add noise, starting from the delta until the asymmetric Gaussian, and then we learn a denoise network to perform iterative reverse process by sampling from the asymmetric Gaussian until we get a sample of the approximation to the delta. And later on, I will introduce several challenges if we employ such a vanilla diffusion model for this ranking task. And different from this vanilla diffusion model, in this work, we actually propose a diffusion-inspired truncated sampler called DITS that align from the text embedding to the video embedding. And our method can actually gradually model the modality gap. And our method is guided by the contrastive loss. So firstly, let's have a quick look at what are the key problems of the vanilla diffusion model. Since the diffusion model needs to access the ground truth data to learn to capture its distribution. So the modality gap for the relevant pairs is generally well known. And ideally, we know that for the retrieval task, the modality gap for the relevant pairs should be 0. And it's well defined by the delta, which is equal to video embedding minus text embedding. But the problem is that in this retrieval task, the modality gap between the irrelevant pairs can be never known. And this poses challenges for the distribution modeling if you are going to use the original diffusion L1 or L2 loss, which means if you are going to use the original diffusion loss to train this diffusion model, it cannot properly handle the irrelevant pairs, but only can access the relevant pairs. So this should be the first problem of using a vanilla diffusion model. And the second point is that we find since the diffusion model starts sampling or reverse process from the random sample of the asymmetric Gaussian, this operation can actually cause some randomness. And this randomness can be beneficial for the generation task because we want to encourage the generation diversity. But for this ranking task, this actually can pose some misalignment. And the approximation of the delta is not that accurate. So our proposed method tries to tackle these twofold problems. So here, corresponding to our proposed method, that giving a text embedding and a video embedding in joint embedding space, for example, both are delivered by clip encoders, and our proposed method called Diffusion-Inspired Truncated Sampler that directly start from the text embedding and do several time steps of the reverse process of the standard diffusion model, and we get the approximation of the video embedding. And we will use this approximated video embedding and original video embedding and put them into the contrastive loss to learn our diffusion model. So as you can see, during this process, we can actually implicitly capture the modality gap at each time step. For the denoising network, we adopt the we tailor from the DIT network structure, and in our work, this is called the alignment network. So two key points of our proposed method is that in response to the two challenges of employing the vanilla diffusion model, the first point is that our proposed sampler actually adopts the contrastive loss to jointly consider the relevant pairs and irrelevant pairs. The other point is that this actually defines a truncated diffusion flow that starts from the text embedding to the video embedding. Let's have a look at the performance of our proposed method. That here in this table, we provide the performance comparison on two benchmark datasets of MSRVTT and LSMDC that we compare with existing SODA methods on different clip variations. As you can see, our proposed method can enable state-of-the-art performance. And the performance gap is quite large. It's a little bit larger, especially for the larger clip backbone. And similarly, we provide performance comparison on another two benchmark datasets of DDMO and VTEX datasets. We also provide some model discussion of our proposed method. Since this proposed sampler performs iterative alignment, such as performing the standard reverse process of the diffusion model. So here we provide a table to discuss the hyperparameter of the time steps. As you can see, when we gradually increase the number of time steps, we can consistently see the performance boost. But if you further increase the number of the time steps, the performance, we see performance drop. So this is because actually, when we continually enlarge the time steps, and the proposed method is so powerful that it actually learns overfits. it learns an extremely precise result. And it sacrifices the flexibility to accommodate for the text data. And so that the result is that it loses the generalization ability on the testing data set. We also provide a table here to discuss the proposed sampler's effect on clip embedding space, that we compare two variants, that whether we fix the clip model backbone or we jointly train our proposed sampler with the clip backbone. As you can see that jointly training involves the best performance, and if we fix the clip in backbone, the performance, there's a large performance gap. And actually this tells us that this actually plays the role of guiding the clip embedding space learning, and it can improve the quality of this joint embedding space. Here we provide more model discussion to the diffusion models. So you can firstly have a look at the table below that we discuss the effect of using the original vanilla diffusion model and compare with our proposed DITS. As you can see, if we pre-train the diffusion model with its original L2 loss, you cannot get promising results. And even if you use the contrastive learning, such as the influence E loss, to fine-tune this diffusion model, there's the performance gap still exists. We also do some very detailed discussion on diffusion, other settings of the diffusion model, such as whether we are going to introduce some conditions to the denoising network. And in our work, we find that the denoise network, or in our work, the alignment network without condition performs best. And this is because since our proposed sampler already starts sampling from the text embedding, so further employ the text embedding as a condition can mislead the learning and can make the model confused. And on the other point, if we're going to use the video embedding as a condition, since a single video can correspond to multiple text queries, introducing the video embedding as a condition can also confuse the learning. And similarly, we discuss how we can define this modality gap, whether it starts from the text embedding or start from the video embedding. And with the same reason, we find that starting from the text embedding enables the effective learning. This is our proposed method. Thank you. Any questions?
Awesome. Yeah, thanks, Jiamian. Yeah, we still have about 5 minutes plus left in the chat, in the webinar. So if you have any question, please put on the chat. I haven't seen any yet, but can you go back to the slide architecture?
Mm-hmm.
We'd love to revisit it. Awesome. Yeah, I remember when you first present at our webinar, is also focused on text-video retrieval, right? Can you explain the differences of this approach versus that previous work?
Can you repeat?
Yeah, can you explain the differences of this work compared to the previous work?
Yeah, actually, when we previously launched our project, if you remember, it's called TMAS.
Mm-hmm.
That proposed method, we want to introduce the diffusion model, but in the end, we deliver TMAS. The difference between this work and previous method is that the previous method is a interaction between the text and video embedding. Mm-hmm. So the focus is to learn on text distribution to empower the alignment. That by introducing a text distribution, we provide more chance to let the text embedding to bridge the video embedding in the joint embedding space. So that's the key spirit of the TMAS. But this work is totally different. Is that, as you can see, this work, there's no interaction between the text and video when we define this diffusion process. So this sampler actually totally serves as a pure representation learning that we propose a iterative process to gradually align the text embedding toward the video embedding. So there are fundamental differences between these two works. And this sampler actually is not a simple add-on for the previous TMAS because they work differently. As you can see, there's no conditions to guide the text embedding for the alignment, video condition to align the text embedding.
So you mentioned in this work, you try to gradually align the text embedding towards the video embeddings, right?
Yes.
And that's the purpose of the modality gap modeling.
Yes. Yes. You can understand that in existing methods, the alignment is a single step. But if you're going to use a sampler, we actually split the single step alignment into an iterative process. That's so that the alignment is performed in a more fine-grained manner. That you gradually, in each step, you align a little bit, and you gradually repeat this process until you find a proper resulting embedding that is close enough to the target. In our work, is a video embedding.
Can you go to the tables with the quantitative results? Yeah, so it looks like you compare with TMAS as well.
Yes.
And I see. It
Yeah,
looks
as
like
you can see,
there are some results it's better than TMAS, but there are some results it's slightly worse, right?
Yeah, actually, if you see on these 4 data sets, you will find that there's only one case that on this LSMDC data set with the smaller cliff backbone that this proposed method fails to beat TMAS. But on the other 3 data sets, such as MSRVTT, also the DDMO and Vtex, especially for the larger model backbone, you can see the performance gap between these DITS and TMAS is quite large.
I see. So this method looks like it's gonna be a better solution with like bigger base model. Is that what you're saying?
Yeah, I would say yes. Both the TMAS, yeah, there's one point that both TMAS and these DITS, they are developed based on the baseline of XPOO, but yeah, they are using the same backbone, but with different modules.
And did you see any like meaningful qualitative differences between TMAS and DITS?
You mean the filling cases analysis or?
Yeah, the qualitative performance.
What do you mean by the qualitative performance?
Yeah, like qualitative, like text-to-video retrieval, right? Did you see the DITS seems to be perform better at certain type of text query compared to like TMAS?
Yeah, actually, I do not provide that kind of the qualitative analysis, if I'm understanding correctly in these slides. But in our paper, we do some analysis to compare the distribution, especially for the relevant pairs, before employing our proposed sampler and after employing the proposed sampler. And we find that the modality gap, especially for the relevant pairs, indeed can be better bridged, which means this sampler can help bridge the gap between the relevant pairs.
Okay, thank you. Great, awesome. Yeah. So what could be the next direction for this style of research? You have done a couple of work in text-to-video retrieval, right? You know, what could be next?
Yeah, I think this is a very good question. I've seen a tendency that the clip model, it has been popular for like 2 or 3 years, and it's kind of out of date. And I've seen a tendency that employing the large language model as the backbone to in exchange for the clip model for the downstream tasks such as VQA or text-video retrieval. Currently, one of my undergoing tasks is that we are training a language model as an embedding model in with the contrastive learning for this kind of task, such as VQA or retrieval or captioning. I think that should be one of the tendency in the future.
I see. So replace the clip based model with an actual multimodal LLM, right? To get embeddings, right?
Yes. I think there are several reasons why we want to replace the clip model with the large language model. And the first point is that the better scalability of the large language model. And the second point is the better reasoning ability of the large language model. And the third point is that we've seen in some works that the large language model can also be seen as the bag of words model. So it should have some much more benefits than we employ this kind of model as the embedding model rather than the clip model.
Yep, awesome. Great. Then final question from Brian. He asks, I look at your GitHub and saw that your code is coming soon. Any estimate on when it might be available?
Yeah, thanks for this question. Actually, this work and our TMS, we're experiencing some confidential issues currently, and definitely we hope we will release this code very soon.
Awesome. All right. I think good time. Thanks again, Jiamian, for spending time walking over your work today. Thanks again to speakers. I think Nahid and Karthik already left, but yeah, Surya, thanks again for presenting. Thanks for attendees for joining as well. The recording of this work should be available within the next few days, so be sure to share it on YouTube with the speakers and post it on our social. So we appreciate you guys spending time this Friday learning about some of the latest research in multimodal AI. And hope you have a good rest of your weekend. Thanks, Jiamian.
Thank you.